So for the scope of our class, we are just going to look at the first type of solutions, which is distinct real solutions when you have a system. And then what ends up following, if you end up needing to do more than that, is very similar to what you do with repeated solutions or complex solutions. But we are, again, going to just look at one set of examples for our class on distinct real solutions. So in the previous video, we showed that this was the solution, and the way in which we can find this out, so I'm going to kind of work backwards in this one, and then I'll show you one more example, is both of these x1 and x2 have the form very similar to what we did with just our first order, second order differential equations. If you notice, they all have this form K1, K2, so like different constants, K1 and K2 here, and then e to what we call lambda, and lambda is what is known as an eigenvalue of the matrix. So it's an eigenvalue of A. And how we find this is you need to figure out the determinant of A minus lambda I and figure out when you have zeros, where I is your identity matrix. And so in this case, for our A, we're going to look at where 1 minus lambda times 1, 3 minus lambda times 0, so is just 3. 5 minus lambda times 0 is just 5. And then 3 minus lambda, where is that equal to 0? And again, those are going to find you your lambdas that then become in part of your solution. So when we find this determinant, that means I'm going to have 1 minus lambda times 3 minus lambda minus 15 equals 0. I'm going to have 3 minus 4 lambda plus lambda squared minus 15 equals 0. So lambda squared minus 4 lambda minus 12. And if I factor this, I get negative 6 and 2. And so these eigenvalues end up becoming 6 and negative 2. And if you notice, that's where our lambdas are then plugged in this problem. The next question is, how do we figure out these k's that make up that k vector? So what we'll do is we'll say, okay, if lambda is equal to 6, then I need this to end up being 0, right? So I need negative 5, 3, 5, negative 3 times whatever this K1, K2 is to be 0. Well, in that case, that means negative 5 K1 plus 3 K2 needs to be 0, and 5 K1 minus 3 K2 needs to be 0. Well, that's only true if K1 is 3 and K2 is 5, or any multiple of that is going to be fine, but that's like the most basic. And if you notice, in front of our E with our 6, that's what you end up getting. You would do that same thing for lambda equal to negative 2. So if that's the case, I have negative 3, 3, and 5, negative 5, K1, K2 needs to be 0. oops, I'm sorry, that should be positive 3. I'm plugging in a negative 2. So positive 3 and positive 5. Okay, so 3k1 plus 3k2. Trying to show you where the solution, I'm just trying to fit it kind of in here. Okay, now that's only true if k1 and k2 are the same number, but one's positive and one's negative. And if you notice, so then we have that right here. Okay, let's look at another example where we're just taking this all the way from the beginning and working all the way through. So we're going to find the eigenvalues first. Well, let's actually first set up our x prime equals 2, 3, 2, 1, x. And there's no f of t functions over here, so this is homogeneous, which is nice. All right, so you need to find the eigenvalues first. So 2 minus lambda, 3 and 2, this diagonal stays the same. 1 minus lambda equals 0. 2 minus lambda times 1 minus lambda, minus 6. 2 minus 3 lambda plus lambda squared, minus 6. So lambda squared minus 3 lambda minus 4. And so that factors into lambda minus 4 and lambda plus 1, which means my first eigenvalue must be 4 and my second one must be negative 1. All right, if that's the case, then 2 minus 4, negative 2, 3, 2, and then 1 minus 4, negative 3, times k1, k2 must give me 0. And this is what we call the eigenvector, okay, that this is going to be the multiplicity in front of that solution that gets me that combination of 0. Okay, so negative 2k1 plus 3k2 needs to be 0, and 2k1 minus 3k2 needs to be 0. Well, that's only the case if, because they're opposite sides, k1 is 3 and k2, I said opposite sides, sorry, opposite signs, and k2 is 2. Right, because they need to be essentially the same number, but just switched so that they cancel out and get 0. So that means my first solution must be 3, 2, e to the 4t. All right, let's do that same process for our eigenvalue of negative 1. So again, I have 2 minus negative 1, so 3, 3. 2, and then 1 minus negative 1, 2, times k1, k2 equals 0. So 3k1 plus 3k2 is 0, and 2k1 plus 2k2 equals 0. Well, that's only true if k1 and k2 are the exact same number, where one is positive and one is negative. And you can make them anything you want. So like, let's just make them something that's like the easiest possible, 1 and negative 1. And so our x2 is 1, negative 1, e to the negative t. Now, if you're like, what if I chose something different for these? That's fine, because our general solution, remember, has that c1 in the front. So if you ended up being like 2 and negative 2 in this, then it just means if we have an initial solution that my C2 and your C2 just might be different from each other. And that's fine, okay? Also, if you chose to do like K1 is negative 1 and K2 is 1, then that's fine. Like our C2 is going to be the same number, but one's going to be positive and one's going to be negative, so that we end up getting the same value when you solve for that initial value problem. So it's kind of arbitrary into like what you call, because once you plug into your IVP, our solutions would end up being the same in the long run, if that makes sense. I hope so.